Hello everyone, now we will discuss on the topic tertiary treatment part 2. In this class we will discuss on membrane processes and content is membrane processes for wastewater treatment, types of membranes, comparison of some site separation membranes, organic and inorganic membranes, principle of working, membrane shape and modules, transport in membrane and liquid diffusion through pores. The membrane processes are physical diffusion processes of particles in water. They function because certain types of membranes allow particles with particular characteristics only to pass through them, and membranes are thin and porous sheets of material able to separate contaminants from water when a driving force is applied. And this method has many advantage, like say performance is very high, it is very compact unit, it requires very less floor area, very less space is needed than conventional treatment schemes, and simple operation. Membranes available can be used to separate many kinds of contaminants, and disinfection can be performed without chemicals, but it has some disadvantage also, like say membrane fouling. The pollutants are deposited on the membrane surface and also in the pores of the membrane, and those are clogged and it loses its efficiency. And production of polluted water, water molecule passes through the membrane and one side we get the permeate and other side we get the concentrate. So, this concentrate or retentate, this other side is called retentate. So, that retentate contains the pollutants and the concentration of the pollutants is very high in that part, and membranes have to be replaced on a regular basis. So, it is costly method basically, and this process can be used for production of potable drinking water from ground, surface and sea water sources, as well as for the advanced treatment of wastewater and desalination. This method can be used for different types of wastewater treatment, basically from home use to very large scale production. Now, we will see the types of membrane. Depending upon different driving forces and division factor, we can have different types of membrane and their operation. Like say when driving force is pressure and division factor is size, we can have filtration, microfiltration, ultrafiltration, nanofiltration. So, where the size will be different for different filtration, and when pressure and concentration are responsible for this, we can have the process that is reverse osmosis, and size and diffusion both are the division factor. And when we use the electric field as a driving force, we can go get electrodialysis and reversal electrodialysis. In that case, ion charge and diffusion both are considered as division factor. And when steam pressure is used as the driving force and then temperature is the division factor for hydrophobic membrane, we can say this is the application for membrane distillation. So, these are the different types of membrane on the basis of application and on the basis of driving force and division factor. Now, we will see the comparison of some size separation, that is pressure driven membranes. So, here the parameters: typical membrane material, pore size, membrane pressure drop, permeate and permeate retentate, that is concentrate. So, pressure driven processes are microfiltration, ultrafiltration and reverse osmosis, 3 have been chosen, and then we will see the difference. Typical membrane material, if we see the cellulose acetate, polysulfone, ceramics in case of microfiltration, ultrafiltration cellulose acetate, polyamides, polysulfone, and reverse osmosis cellulose acetate, aromatic polyamides. That means, the materials are very similar, but pore size is different. In case of microfiltration, that is 10 to 0.02 micron size, where ultra this is 0.02 to 0.001 micrometer size, and reverse osmosis 0.001 to 0.001 micrometer. So, we are seeing even very small particles or molecules or the pollutants can also be arrested here or be separated here in case of RO. So, certainly it will be requiring different pressure, that is in this case membrane pressure drop PSI 1 to 10, here 10 to 100 and 100 to 1000, and permeate in this microfiltration maybe water and dissolved molecules, and ultrafiltration water plus small molecules, and reverse osmosis only water. Even small molecules are also not able to pass through, because the pore size is very small, and retentate water plus large suspended particles for microfiltration, water plus large molecule for ultrafiltration, and water plus solutes. Even the solutes are also not able to pass through the pores in case of reverse osmosis. Now, we will see organic and inorganic membranes, different types of membranes and their applicability. Normally, the organic membranes are applied in lower temperature and inorganic membranes are used at higher temperature. So, some examples are given here, that is cellulose diacetate and PA, that is polyamide, aromatic and aliphatic, and PI polyimide, and PS polyether sulfone, PS polysulfone, PVDF, that is polyvinylidene fluoride, and here we see the maximum temperature range this can be used. And for inorganic membranes, that is Al2,3, silicon carbide, ZrO2, TiO2, we see the maximum temperature range is much more than these organic membrane, and this can be used for a wider pH range. Okay. So, these are the different available membrane materials, and here the structure of some organic membranes are shown here, like say PES has this type of structure, PS has this type of structure, PVDF has this structure, and these are the different polymer name and their acronym which have been applied for different applications, not only for water treatment, that has been used for different application. Now, we will see the principle of working and some important terms. As mentioned, in this process feed mixture is passing through the one side of the membrane, and other side the sweep is sent as optionally, otherwise the water will be passing through it, the membrane, and then the pollutants will be arrested here, that will not pass through. So, this part which we are getting, that is we are getting retentate or reject, and this is concentrate, and here we are getting the penetrate. So, pure water will come here and pollutants will be available in this concentrated here. So, this is we are getting retentate and this is we are getting penetrate. So, this is the mechanism. Then how this water is passing through the pore size, the molecules of the water size is lesser than the pollutants. So, pollutants are being arrested. So, water is going there. So, different terms we are getting, that is retentate, part of the feed that does not pass through the membrane, permeate, part of the feed that passes through the membrane, sweep, liquid or gas used to help remove the permeate, and the barrier is most often a thin non-porous polymeric film, but may also be porous polymer, ceramic or metal materials, or even a liquid or gas, and the barrier must not dissolve, disintegrate or break. So, these are the essential conditions for the operations of this membrane process, and some characteristics are that separating medium is semi permeable barrier. So, this medium is semi permeable, that means some material will be allowed to pass through and some will not be allowed to pass through, and a sharp separation is often difficult to achieve and low energy requirements. So, these are the characteristics of this membrane process. Now, we will see the membrane shape and modules. So, membrane may have different geometry and different shape, like say flat, asymmetric and thin film composite membrane, tubular membrane, hollow fiber membrane and monolithic structure. And there are 4 major types of membrane modules, that is plate and frame module, spiral wound module, multitubular membrane module and then hollow fiber membrane module. Now, what is the module? So, membranes we see which is used for the separation of the pollutants from it, and this is very thin layer of some material, organic or inorganic material, and the module is a complete unit composed of the membranes, a housing, feed inlet, concentrate outlet and permeate outlet. So, this is a complete module and membrane is an important part. Now, we will see the common membrane shapes. So, we have seen there are 4 important membrane shape, that is flat, asymmetric or thin film composite. Here we see the thin active layer here and this is porous support. So, we have porous support and active layer is our main fiber material, and typical dimension of 1 meter by 1 meter by 200 micrometer thick with a dense skin or with dense layer 500 to 5000 Armstrong in thickness. So, that is I told you that it is a very thick layer, very thin layer with this material, membrane material. And then we see the tubular. So, we have feed inside and from the outside we are getting the permeate and from the inside we are getting the reject or the retentate. Okay. So, in this case what will be happening? It typically 0.5 to 5 centimeter in dia and up to 6 meter in length. Thin dense layer is either inside or outside surface, either outside or inside we have a thin layer of the membrane material. Okay. So, porous supporting part is fiberglass, perforated metal, etc. So, this is the tubular membrane shape, and hollow fiber, here we see this is our fiber bore and thin active layer, and we have a porous support. Okay. So, typically 42 micrometer ID by 85 micrometer OD with a 0.1 to 1 micrometer thick dense skin. So, this is a hollow fiber membrane. The hollow fiber and tubular, these are basically differ on the dimension also, and then monolithic type shapes is also available, and this is basically for inorganic oxide membranes. So, this is the honeycomb we see here. So, that monolithic element for inorganic oxide membranes, both hexagonal and circular cross section is available. That may be this cross sectional circular or hexagonal as shown here can be available. So, we have a membrane and these are the channel and porous support. So, we get permeate from this. So, this is the membrane shape, and then membrane module we have plate and frame module. That is a plate and frame, just like plate and frame filter press, we have some one frame and another plate, inside we have some membrane. So, that is one enlarged tube. So, we have a tube, the porous tube, and then either inside or outside we have a membrane. Okay. Then feed flow, if it goes inside, so we will be getting permeate from the outside of it, and then hollow fine fibers. So, here also the similar way, the dimension is different in tubular and hollow fiber. We get here the feed water is coming from the outside. So, from the inner side we will be getting the product, and spiral wound, this is an example of spiral wound. So, here feed flow in that direction, and then from the inner side we will be getting the penetrate, and these are the different permeate side backing material with membrane in each side and glued around edges and to center tube. So, this is the permeate flow from the out to inner, and then we are getting the permeate from the inner side of it. And these photographs, now we will see some photographs and the concept will be more clear. Now, some example of plate and frame module, most lab scale membrane modules. So, this is one. So, this is your plate and frame. So, that is Ovivo USA LLC, their product, and MBR membrane bioreactor also we have this plate and frame type module, plate and frame module of the membranes, and this is another example. These are also the plate and frame type of module. Then spiral wound module, you see here how it looks. So, this can be used for brackish water and seawater desalination and for treating the wastewater of food and dairy industry or distillery industry. So, this type of spiral wound module is used. So, here you see this is our penetrate and this is our feed solution. So, that will be our permeate collection material and feed channel spacer and membrane is here. So, again we are seeing membrane and feed channel spacer. So, which water inlet water is coming here. So, it will be from outer to inner side it will move, and from the inner we will get the penetrate, okay. And this type of arrangement is there, that is called spiral wound module. And then tubular modules. So, mostly ceramic, but also polymeric and mono or multi channel it is possible, and waste and drinking water, food, biotech, for the production of biotech application these modules are used as shown here, okay. Hollow fiber module. So, that is used for drinking water and wastewater treatment, and you see here these are the hollow fiber. So, number of fibers are taken here. So, water may be going from the outside and then from the inner side we will be getting the permeate, the treated water. So, this type of modules are available for different applications for drinking water and wastewater, also for the production of drinking water and treatment of wastewater as well. And this figure shows us how the hollow fiber modules work. So, here the influent may be through the inner part of the hollow fiber. So, the penetrate will come out from it. So, then this will be our waste or retentate, and this is in out mode. So, influent from the inner side of the hollow fiber and from the outside we are getting permeate. Maybe on the reverse case, this may be going from the outside and from the inner side we can get the permeate. So, this is our effluent and this is our influent is coming here and we are getting the permeate here. So, that is out in mode. So, these are the fiber. Now, typical characteristics of membrane modules like say plate and frame, spiral or wound, and then tubular and hollow fiber. So, packing density meter square per meter cube. So, 30 to 500 for plate and frame, 200 to 800 for spiral or wound type, and tubular type 30 to 200 and 500 to 9000 hollow fiber. So, hollow fiber we see we get much packing density with respect to other, and resistance of fouling in plate and frame good resistance, and spiral or wound moderate, tubular very good resistant, and then this is poor resistance. And ease of cleaning, again ease of cleaning is good for plate and frame, after certain interval we can change it. Spiral or wound, that is fair, and for tubular excellent, and for hollow fiber it is again poor. So, relative cost very high cost for plate and frame, spiral and wound it is low cost, tubular high and hollow fiber low cost. And main applications, so distillation, reverse osmosis, ultrafiltration, microfiltration for plate and frame, for spiral or wound distillation, RO, UF, MF, and here for tubular RO, UF, and D RO, UF for hollow fiber membrane module. So, these are the different applications, and we can get some advantage and disadvantage of all these type of modules, like say plate and frame for both organic and inorganic membranes. The advantage is possibility to analyze permeate at each stage, but low packaging density, this is the drawback. So, spiral or wound, that is organic membranes only, this is not applicable for inorganic membrane. So, high packing density, low cost, and cleaning in place is difficult to handle, and pre-treatment is compulsory, and tubular type for both organic and inorganic membranes it can be used, and then limited pre-treatment, well adapted to cleaning in place, and low packing density, high energy consumptions are the drawbacks, and hollow fiber mostly organic membranes, and then very high packing density, low energy consumption and low cost are advantage, and pre-treatment compulsory for in out mode. So, this is the drawback of it. Now, we will see the transport in the membrane. So, what is the mechanism for the transport of the liquid and gas molecules through a porous membrane, that we will discuss here. So, we are showing here different situation when the pollutants and gas molecules or water molecules both are passing through the pores. So, that is A, that is bulk flow through pores. So, in that case we are not getting the efficient separation of the pollutants from the water, but B is diffusion through pores it is diffused. So, but C restricted diffusion, and here some other type of mechanism is possible, that solution diffusion through dense membranes. So, dense membranes, not we are considering the pores, that is solution that is coming inside it and it is being diffused. So, that way the smaller size molecules or which is having more affinity with the membrane material, they can pass through it easily with respect to other molecule. So, that is the mechanism for the purification of the water or the removal of pollutants from the water. And now, we will see the bulk flow. So, in this case bulk flow. So, bulk flow of a fluid due to pressure difference through an idealized straight cylindrical pore. If the flow is in laminar regime, which is almost always the case of flow in small diameter pores, the flow velocity V is given by Hazen-Poiseuille's pressure drop. That means, it is a flow through pores or porous media. In that case, the Hazen-Poiseuille's equation can be applied, that V is equal to d square by 32 mu L into P O minus P L, where P O is the inlet pressure, P L is the outlet pressure, D is the pore diameter, mu is the viscosity of fluid, and L is the length of the pore. Now, if the membrane contains n such pores per unit cross section, so if you have a membrane unit cross section, if you have n such pores, okay, of membrane surface area normal to flow, the porosity of the membrane is how much? Pi r square for a single. So, pi d square by 4 for a single one. So, n into pi d square by 4, that is the total surface area covered by this pores, and total surface area of the membrane is 1, we have assumed. So, the void fraction, that will be the volume of the pores divided by volume of the filter. So, if we take the unit length once again, so 1 into 1 the 1 volume, and this will be n into pi d square by 4 into 1, that will be the volume of the pores. So, E is equal to volume of the pores by volume of the membrane, that is equal to 1. So, n pi d square by 4, that is equal to void fraction. Then the superficial fluid bulk flow flask, that is mass velocity, okay, n through the membrane is n is equal to this V into rho into epsilon. So, we are considering unit cross section. So, n is the mass flask. So, that is why unit cross section is considered. So, unit cross section into V into E, that is the volume for the void into rho. So, that is the volume of the flask, because the water will be passing through the void space only. So, that is equal to, we will replace the value of V now with the Hazen-Poiseuille expression. So, V equal to, we will be using d square by 32 mu L into P0 minus P L. So, we are using this, and here rho into epsilon, rho into eta E, rho into E. So, this one. So, now we are getting, replacing this E value, we are getting phi n rho d to the power 4 128 mu L m into P0 minus P L. So, this is the expression for the n. Now, L m is the membrane thickness and rho and mu are the fluid properties. So, in real porous membrane, pores may not be cylindrical and straight, and hence pore diameter is replaced by the hydraulic diameter. So, this is one consideration we assume when to represent the real situation. So, d will be replaced by dh, dh is nothing by 4 into volume available for flow by total pore surface area, and if we divide both numerator and denominator by membrane volume. So, this is the top part, total pore volume by membrane volume is equal to E, and total pore surface area by membrane volume is equal to A. So, this A can be correlated with the specific surface area like this, specific surface area is equal to A by 1 minus E, because the AV, the specific surface area, is the surface area per unit volume of membrane material not including the pores. So, when we are considering the pores, then that will be AV equal to A by 1 minus E. So, we will be putting this d in terms of dh, and dh is in terms of 4 E by A. So, then n value comes as rho E cube P0 minus P L by 2 1 minus C square tau A V square mu L m. Why this tau? Because in this case the L m which we have considered, that may not be, the pores may not be a straight line. So, one tortuosity factor is consumed as tau. So, this is the flux through the pores. Now, we will discuss liquid diffusion through pores. So, diffusion through the pores of a membrane from a fluid feed to a sweep fluid when identical total pressures, but different component concentration is there. Here pressure difference is not there, only concentration difference is there. So, in that case we can consider that Ni transmembrane flux, that is equal to dEi by Lm into CIO minus CIL, when Ci is the concentration of I in the pores at the two faces, that is inlet and outlet, okay. And dEi is the effective diffusivity, and then dEi can be calculated by this formula when E into di by tau into KRI. So, di is the ordinary molecular diffusion coefficient of the solute I in the solution, and E is the volume fractions of pores in the membrane, and tau is the tortuosity, and Kr is restrictive factor that accounts for the effect of pore diameter dP in causing interfering collisions of the diffusing solutes with the pore wall. When the ratio of molecular diameter dm to dP exceeds about 0.01, then Kr plays a significant role. Otherwise, when you see dm by dP is less, is 0.01, in that case Kr is 0.96. So, this value is almost 1, this Kri value is almost 1, but when this value is increasing, dm by dP is increasing, that means dm size is increasing, then 0.3. So, Kr 0.24, and when dm greater than dP, then Kr equal to 0, that means there will be no diffusion of the material. So, we will see one example here. Find the flow rate of a water in meter cube per meter square per day when it passes through a porous polyethylene membrane by a pressure differential at 70 degree centigrade. The membrane is of 25% porosity with 0.3 mm diameter pores and a tortuosity of 1.3. Pressures on either side of the membrane are 500 kilopascal and 125 kilopascal. Assume membrane is 1 micron thick and flow is fully developed laminar flow. So, we have the formula for laminar flow that Q by AM, we have to calculate that flow rate in meter cube per meter square per day. So, that is Q by Qm, that is equal to N by rho, and this formula we have used in our previous discussion. So, here we have to calculate this one using this formula. So, the values are given at 70° mu of water is given this Cp or this equal to Pascal second, and rho is equal to this, and Po is equal to 500 kilopascal. So, this 5 lakhs Pascal, and PL is 125 kilopascal. So, 1,25,000 Pascal, and E is equal to 0.25, D equal to 0.3 micrometer. So, 3 into 10 to the minus 7 meter, Lm equal to 1 into 10 to the minus 6 meter, that is 1 micron, and tau is equal to 1.3. So, by putting this value here, we can get Q by AM is equal to N by rho, that is equal to 0.25 into 3 into 10 to the minus 7 square into 5 lakhs minus 1,25,000 divided by 32 into 0.42 into 10 to the minus 3 into 1 into 10 to the minus 6 into 1.3. But this is the Q is not in day, that is in second. So, here we have to convert it into day. So, these are the conversion factor multiplied by 3600 into 24. So, it is becoming 41,724 meter cube per meter square per day. So, now we are able to solve the example. Up to this in this class, thank you very much for your patience.